run that container again. Oh, thank you for starting the recording. I totally forgot to do that. Then it just shows the version of Python. But we could also, for example, in the same way with the other containers, we'd be able to log into it. So we add .sh -it, and we're in the container with the Python 3 command installed in there and available for us to use to do whatever we want with, if we wanted to do that. Okay. And if you remember, I also said that from this Dockerfile, each of these actually corresponds to a layer. Now, of course, the Alpine one already consists of multiple layers as well, so there may be extra layers in here. But each of these are what we got is a layer within the container, which is the file system superimposed on top of each other. So, okay, yeah. So there is, okay, Jeremy's asked a bit more about the file. Okay, I realize there's some confusion in terms of knowledge there. So when we build a container from the Docker file, we tagged it with our username, okay, and that's what we were talking about before. And if you want to push to Docker Hub, then your username will be incorporated somehow, even if you don't specify it at build time. The Docker file itself is just called Dockerfile. That's the default name, and the container itself, that's not the name of the file with the container in. Okay, because it's actually saved within Docker somewhere within the Docker daemon and the Docker service somewhere. That's all managed for you, so you don't actually see the file name. Now, when we come to talk about reproducibility, we'll show how you can actually export a container to a real actual file that allows you to save it for future reference without pushing to Docker Hub where things may be more transient, and how to re-import that container file back into Docker itself. So we'll cover that a bit later on, and then file names do matter. Okay, so we built our container, and when you're building your own containers, there's a few sort of tips and tricks, or things that are sort of at least semi-obvious but are worth pointing out, right? So when you're coming to create your own containers, there's a lot of choices to make, right? And how do you decide? And we'll talk later about how we decide about how much you encapsulate in the container and how many, or whether you produce multiple little containers, each with a slightly different service in, or a slightly different bit of software in. And we'll talk about that. We'll cover that in more detail later. But there's some top say to start smart. Don't install everything from scratch, right? If Python is core to what you're doing, start from one of the Python distributions. Don't start from Alpine and then have to add your own Python and all this sort of stuff from the top. The same with R. And we've used Alpine Linux a lot because it's quick to download, but often people use more fully featured distributions, Ubuntu, Debian, CentOS, these sorts of things to start. If the software you're installing has some sort of association with a particular flavor of Linux, then it's often useful to start from that flavor of Linux. We'll talk about the how big a bit later on in terms of whether you bundle everything into one container or whether you make multiple containers that you then orchestrate together. As you've seen from what we've done already, one of the key things you end up doing is installing software from the Linux distro repositories. So in that terms, it's it's APK for Alpine, which is a bit odd, but you need to know for the flavor of Linux you're using how you get and install packages. So things like APT for Ubuntu, Deb for Debian, Yum for CentOS, and Zipper for SUSE. And if you don't know quite what it is, you can always search, or you can ask colleagues or somebody helpful like that. Use what you know and leverage your own knowledge. If you do things and install them on your own system with things like pip or install packages in R, then these all also work at the containers. So reuse that knowledge and build things that way. You may need to use the APT or apt-get things in the first instance to get pip there, unless you're starting from one of the Python containers. But once you're there, you can do that. And look for instructions for, if you're installing things into a container, it's always Linux. Okay, so first approximation. I think Windows now supports Windows containers, but in terms of this sort of stuff, it's always going to be Linux. So you're always looking for the Linux install instructions, and make sure you read through what you're going to do beforehand. So, you know, really, rather than starting out and just adding things and seeing how it goes, it's usually better to have a bit of planning and have a bit of think about what you need to do and what your strategy is for installing software and using containers. And we'll talk a bit more about this in the reproducibility stuff again. Okay, and then you can create a Dockerfile and have a go and iterate towards the container builds, right? So now the next thing we want to do, we're going to show you how we take our container that we've built, our own one, and we push it up to Docker Hub so that other people can use it, or you can point at it in a way for other people to use. Now, this isn't the same as making something recorded for posterity or some sort of reproducibility purposes, because things on Docker Hub are typically ephemeral. But it is a useful way for being able to distribute containers and code in an active project that you're working on. So there are limits on what you can do with a free account on Docker Hub. You know, there are limits of number of downloads and how long containers can live while being inactive within the Docker Hub. But for the purposes of this course, we can use the free account to show exactly how it works. So the opposite of Docker pull is Docker push. So I'm going to take the container that I was using before, and I'm just going to use my command again and use Docker push, the name of my container image the image I created. Okay, and it tells me it refers to something, and then it uploads the different layers of the container. The container image. See, this is the problem. I always have this problem when I'm talking about containers. Because container, the terminology in sort of colloquial conversation is used quite loosely. Right, and I do try to be more disciplined in using the word image and container or container image, but I do slip up sometimes because people just tend to use the word container, and so sometimes it helps if you're speaking to people to be a bit clearer about, you know, whether they're speaking about the container that's running or the image that the container is built from, and be a bit careful with your thing. So this has taken quite a while because my upload speeds are slower because I'm working also teaching this lesson. So ARCHER2 is you say you got the error denied, requested access to resources denied. Is that when you try to Docker push? Fine. Okay. So I think that means that that usually means that you're not logged in to Docker Hub from the command line. Yeah, if it's Linux, usually the logins are a bit more manual. Okay, so you should be able to check with the icon in the toolbar as well to check you're logged in up here, and it should have your username listed here with the option to sign out if you're logged in. If not, there should be an option to log in, or you can use the command line Docker login as well. And also Jose asks, why would you upload your container instead of uploading your Dockerfile? Okay, that's a good question, because the Dockerfile is small, right? That would take me seconds to upload. The difference is that once my container is uploaded to my container image, is uploaded to the Docker Hub, people can use Docker pull to just get a copy of the container and run it in that way. Rather than if you can distribute your Dockerfile to somebody, they would then have to build the container image themselves locally using a Docker build command. Okay, you couldn't just pull it out of you don't have the convenience of just pulling it. So it's like the difference between distributing source code for your application, I guess, and distributing a binary that people can just install and it just works. Is the sort of philosophical equivalence of it, I think. Okay. So yes, so people often put things like the Dockerfile into Git repositories if they're part of the project or something like that, where you can track changes in the Dockerfile because it's just a plain text file and make sure it's correct, and then people can get the right version and build their own container that way. But to make it available for people to use with Docker pull or Docker run automatically, then it needs to go up into an online repository of images. Okay, I hope that helps explain it a bit. Okay, so we've now pushed this up to the Docker Hub. So if I go and look at, so this is where I'm going to show my, oops, sorry, you see I was searching for Docker. You can see I was searching for Jekyll on Docker Hub, where you'll see why later on in the lesson. But let me just use that link and go to my things over here so I can look at my content under my account. At some point, it's actually going to respond to me. Sorry, this is why because I don't usually go here. And there you go. So if I looked at, sorry, I clicked the wrong thing. If you click on the repositories tab up here, if you're logged in the Docker Hub online, you can see the image I pushed from the command line. I can click on that and get more information. I haven't added any documentation on it or anything like that. So the information here is quite sparse because there's no description, but these sort of things can be added if you want to use them, and it's usually good practice to add useful documentation to help people who are downloading them, or to give some context for why that image is there. So here's sort of what I was asking earlier. You don't have to name your containers using this naming scheme. You can call them what you like locally and refer to them by the names you choose. It's only when you share it up to the Docker Hub that it needs to have the correct format. And you can always change the name of something. So if you've already called it something locally and you need to rename it into the username container tag format or something like that, then you can use the Docker tag command to do that, to allow you to push up. So you could work locally without the full name and then tag it before you push it up to the Docker Hub and things like that. So, and you can always have different tags and different names for even for the same container image if you're working on if there's a stable version and a development version, for example. Okay, so that's the end of that quick. So we finished off that section from this morning, or before lunch anyway, where we looked at building images. Next, we're going to go on and have a look at building some more complex images. In particular, the thing we haven't covered so far, which we're going to cover in this next section, is how we expose data from outside the container to the container, okay, which is going to be key to be working on. At the moment, we've worked with everything self-contained within the container universe itself, which means we haven't had access to data from the outside world, which is generally going to be what we want to do when we're using containers for any sort of real work. So, as I said, to be able to use your own containers, you need a bit more information than what we've covered. You need to use data from outside the container almost always, right? Because you're going to be operating and doing some analysis on data. You're going to be manipulating data in some way. You're going to want to save output from the work that you've done in the container, in the containers that you're using. Now, as we go through, we're going to have sort of more examples, and in this section of the course in particular has a lot of information in it, right? So I wouldn't expect to remember all this the first time around, but hopefully you can come back and look over again and play around with things and get a feel for what's going on here. We've got some more complex, some different examples at the end to show you what's possible. So let's, from where we unzipped before, we're going to go to a more complex example, which is the sum example. So I'm here in the basic example, so I'm going to go up a level and then into the sum subdirectory. Okay, and there's two things in here. There's the Dockerfile and sum.py. And let's have a quick look at them. The Dockerfile is similar to the one we had before, the template we had before, which has nothing in it. Really, it's not a real Dockerfile. It's just some sort of example. And if we look at sum.py, it's a very simple Python program. Doesn't matter if you're a Python programmer or not here. Essentially, it sums any number of arguments given on the command line. So if I do, I've got Python installed locally. I haven't tested this, so hopefully it works. So I can add up any sorts of numbers we give on the command line and return the sum from them. Okay, so it's a simple example program, but the key here is that this example program that we might want to use in our container is not in the container. It's on my host computer at the moment, and that's what we're going to look at through this session. Okay, so the first question is, what command would we use to run Python from the Alpine Python container? And we can try running it here. So we've got a container. We've got our Alpine Python container. It's got Python in it. Can we run it on the Python to run this Python program? So let's do a Docker run Alpine Python sum.py. Sorry, Python 3. Okay. Oh, that's a bit weird. I've done something stupid, is what this is telling me. Because, okay, I didn't call it Alpine Python. See, that was my first mistake. It's eternally PCC Alpine Python. Okay, so let's try that again. Okay, try it again with the correct name for the container this time. Okay, so the problem is that it can't find the file sum.py, and that's all I alluded to already, right? That file is on the host computer, not on within the container itself. Okay, and in order to be able to use the Python inside the container and our Python program or script outside the container, we need to create a link somehow between the two, either make that script available inside the container by making it visible or by copying it into the container. So the first way we're going to do it is by making the files from our host computer visible inside the container. And this uses what's called a mount, which comes from, I guess, the old-fashioned terminology where you'd mount a disk somewhere or external hard drive. And so we're going to create a mount that maps the data in our computer, this directory in our on our host computer, into the container so it can see the file. And what we're going to use is this command here. So the -v is the option to Docker run that says to create a mount, and it takes 2 bits separated by a colon. What the first bit is the location on the host computer, okay, and the second bit is where that's going to be mounted within the container itself, where that's going to be mapped to within the container itself. These are both file paths. In Linux and PowerShell, this thing here refers to the prints working directory. That prints the current directory. So if I, so my current working directory is this home teaching 2018 blah blah containers Docker intro sum, and if I print the contents of the pwd variable, it's the full path to this location. So what this is doing here is a shorthand way of specifying the full path. I could just not have the $pwd and use this whole string instead, but that's a lot to type. I mean, I could copy and paste it, but it's a lot to type. Whereas $pwd always refers to the current working directory, and that's a shorthand way of doing that. So let's try that command again, and this time we're going to add this option to mount the current working directory into /temp temp within the container. So I'm going to go back to my previous command. I'm going to add -v $pwd /temp. Okay. And we can try and run that again. It took a bit longer to start up because it was doing the mounting, but we still get the same error. It can't find sum.py. And the reason for that is that what is the location of this sum.py file? in the container itself? Well, because we've mounted our local working directory into /t/temp, the location of this script is actually /temp/sum.py, right? This is the subtlety here, is I need to tell it exactly the path in the container, because when I come into the container, in fact, I can show you this. So let's do this run. Instead of the Python free sum.py, I'll get an interactive shell in the container. Oops, and that's not going to work, of course, because I forgot my -it as well. Okay, to make it interactive. Okay, so now I'm in here. Where am I? I'm in slash, and sum.py isn't here. But if I go into temp in the container, then sum is there, and Dockerfile, because they're both in my current directory. Okay, so what I actually need to do when I want to run this is specify the full path to tell it where to find that script. So let's do that. Let's see what it says this time. Okay, so this time it's worked. We've got some output from our script, which is sum0, which makes sense because we didn't add any things to sum. So okay, and the sum's 15, and this time sum of 4, 5, 6. So yeah, just in the case of the host folder, or is it a copy of its contents? It's actually the host folder. So if I modified the file sum.py within the container, that would modify the actual. That's what the same as modifying the actual file. Okay, it's just the amount tool passed through. Okay. Okay, so we've been able to map this file into the container and then use it as if it was part of the container. Use the Python within the container to run the Python program that's actually on the host computer in real life and get the output out. Okay, so now this is where you start to see where containers are more powerful, right? Because you can start to use containers to package up the software that you can then use to act on the data that's stored on your host computer or elsewhere, wherever the host computer it is. Okay, so that's where we got to there. So, so we've managed to get to this with the Docker run command and put the. You got the error that the file could not be located. It may be that the $pwd is not working correctly on Windows. That has happened occasionally before. More recent versions of PowerShell support using Linux like variable names, which is the $pwd. But you can always put the full path in if you need to anyway, as well, if the shorthand doesn't work. Yeah, so when you do that, what's in /temp? If you ls/temp once you're in the interactive, that's the question. That'll see if the file's being mapped in, or not properly. Okay, I've been speaking for a while now since we started. So our Docker command now is quite long. If you look at my Docker command here, I wanted to take a moment to make sure that you understand each of the steps, because we've added to it as time's gone on. I'd like you to take a moment to just think about the steps and make sure you understand what each of the bits of that command is doing. So that's what the next exercise is, and we'll just spend maybe 3 or 4 minutes on this. Is, our Docker command's got one. Can you go through each piece of it and explain what it does, and how would you characterize the key components of a Docker command? Just think about it for a couple of minutes, and then we'll go through the solution together. But try and do it. Think about how you'd explain the different components of that Docker run command to somebody else who'd got to this stage in the course. Again, what they mean before you go and have a look at the solution. So what I was going to say was, I think this seems like a really simple exercise, and I'm not trying to patronize people here, but we have been building up the level of complexity of the Docker command. And I just wanted to pause to make sure that everybody appreciates what we're doing here. I think this is a useful exercise for doing that. So the different parts of the command are the Docker run, which uses Docker to run the container. There's the
the option to mount the current working directory, for which the shorthand is $pwd, to a folder or directory inside the container called /temp. There's the name of the container to run, and then there's the commands we're going to run in the container, in this case python/temp sum.py. But generally, all the Docker commands have this sort of structure. So there's usually the Docker to kick it off, to say we're using Docker, what action you want to take. In this case, it's run. The options that you're going to provide to Docker. In this case, we've already got the one option, which is the option to mount inside the container, but you've also already seen the -IT option for interactive containers, for example. So there are other ones there. The name of the Docker image you're going to use, and the command to run inside. Now, the command to run inside can be a bit different depending on how the container is set up. At the moment, we don't have a default action other to print the version of Python, so that's not really useful. But if I'd set the default action inside this container, for example, to be the Python3 command itself, then this command could have been shortened. Instead of having Python3 there, it would automatically do that bit for me. I could just give the name of the script to run. And if I didn't give the name of the script, it would just drop me into the Python interactive terminal to work for. Okay, so we'll see lots of more complicated Docker commands as we go on throughout the things. And Stefano kindly answered the question from about private repositories. And if you, yes, you have to pay if you want lots of private repositories, essentially. And there might be an educational version of Docker Hub 2. I'd have to check that. That means you can get private repositories for a lower cost. Okay, this we already did, the extracted jobs. We went and looked inside the container, CD'd into temp and ls and showed what was in there. Now, this works well, as we said, if you want to run the software inside your container on lots of different input files, okay, which is often what you want to do. But there are some situations where you want to create an authoritative version of your data and potentially scripts or analysis programs or things like that within the container permanently. So they're always that version is always available to anybody who's using that container that you shared it with. And that's what we're going to look at now, is how you do that. So that's how you copying data into the container at build time rather than making data available in the container at runtime. Okay, so build, sorry, that was me being fast and loose with the terminology again. How do you copy data into the container image at build time rather than make data available within the container itself at runtime? Okay, so say we want to, we finished developing sum.py. We think this is a great version of a piece of analysis tool. You know, we can add together more than two numbers. Who wouldn't want to be able to do that? So let's try and build it into the container ourselves so we can send this amazing, insightful piece of software to other people and let them download it and use it. So we're in this directory. So let me get rid of that. So we're in this directory. We've got our sum.py script. We haven't even created a new container yet. We've been using the Alpine Python container we created in the last session. But what we're going to do is we're going to update our Dockerfile to build in the sum.py into the /home folder within the container image. Okay, so that means in addition to what we did for building our container before when we made the Alpine Python 1, we're going to have an extra layer command, which is this copy, and it's going to take the sum.py and push it into /home in the container image. Okay, so what we're going to do is the Dockerfile here is empty, so we can type out everything again, but actually the easier option is just to copy our Dockerfile from the basic one to here and then edit it to add the copy file. So I'm going to take the basic file and move it here. So let's see. So that's the Docker file we had before making our Alpine Python Docker image. Okay, and now I'm going to edit this. Oops. And okay, so this is my other one. And now, after we've installed Python, but before we set the the default command, we're going to issue the copy command, and we're going to take sum.py and put it in /home inside the container image. So this takes it from our current location, current working directory, and built it into the image in this location. Okay. And another thing we might want to do here, so let's do this. I mean, this isn't we don't do this straight away in the lesson, but we could also make the default command I haven't tried this. This is live demo, how to break your live demo in one go. So this should set the default command to be to actually run that script within the container. So let me save that. Okay. So this is very similar to the other Docker command. Let's build this container now. So we're in the right place. We've got sum.py there. We've got our Dockerfile there. It's the right Dockerfile. It's got the copy in. So we're going to do the same again. We're going to do Docker build. And it's T. You need to give it a different name. Than we had before. And we need to remember to put the dot on the end to tell it we're building with the Dockerfile in this directory. So let's try that, see if it works. We'll see if I've broken it by now. So one thing you'll notice, it was very quick this time to build compared to the last time, but it took a long time because it downloaded everything. And the reason that's there, so /home is in the container. Okay, so Cedric. So Cedric's asking, is the /home in the container or in the host? It's in the container. So as for most of these things with paths, the first path is the host, the second path is the container image. So this is taking it from our local directory where we're building the container and dropping it into home on the container. If home doesn't exist, it will create the directory for it. Okay. And the building was much quicker because it used the cache that was already there for these images that it built already in the same way. Okay, so everything was much quicker, and it's given me a new container, I think. So let's do Docker. Sorry, not the container image, Docker image ls. And you can see now there's the Alpine someone as well. Okay, so let's try running that. You can take a new image you've created. Let's create a container from it and run it. So Docker run that one and see what happens. It takes a moment to start up. It says it can't open the file sum.py, and that is because I did something silly in my Docker file. Right? You should never do change to the live demo in flight, because what have I missed here? I've missed the error we talked about before. Because it's not in the same directory, it's in home, because that's where we've put it, and that's where I made my mistake. So let's try that again. I can rebuild. I should be able to rebuild the image, hopefully. Okay. It was quick again because it's everyone. You'll see I now have an orphan image, which was my previous image, which has now been untagged because I stole the tag for the new version. So you could remove that at some point if you wanted to, but it tends to clutter things up. So let's try running that image again now. I did wrong before. Hopefully it's fixed this time. Okay, so now it says sum equals 0. That's because I haven't given it anything to sum up. So let's try give it some numbers this time. Oh, I've done something horrible here, I think. Why have I broken it? It's like the variables being interpreted by my shell rather than by the container. Let's try that instead. No, it doesn't like that either. Okay, so this is what happens when you don't test what you're doing before you show it to people in a course. Okay. Yeah, the numbers I've entered are sent to the shell after Python has finished running. Yes, you're right. Okay, so that's the problem. So that was why building that as the default command was not the right thing to do in this case. Okay. So I can fix that again. So I made a silly mistake. I shouldn't have done that. So let's put that back to Python 3 right version.
Yeah, can you actually explain what went wrong there?
What went wrong? So what was happened was the container ran the command I had before, which was Python 3 sum.py. So it ran that command perfect as it was supposed to do, and then it finished running the command, and then it said it's got input 789. Oh, I don't know what to do with 789. They don't seem like commands to me. So it didn't know what to do with the 789 command. So here you can see, let me go back to the thing. It said exec the command 7. I don't know what that executable is. I don't know how to execute that command. Okay. So what it tried to run, instead of running, let me type this in the command line, even though we'll give an error. Instead of trying to run this, okay, which is what I wanted it to run, it ran this. Okay, and it never got to the 789. Okay. And because I'm in Z shell, it's popping me around with different directories. Because it knows what those commands sort of mean in Z shell on my local system. And so it didn't know what those commands were. And then it complained that it didn't know what those commands were. Yes, I think you'll need both command and entry points. You're right, Elena, but we'll look at that in a moment. Okay, so that was me trying to be too clever in one go in a live demo. So actually what I should have stuck with was Python minus version here. And going back and building it. If I can get back to the build command, should be very quick. Again, and then if I now do that, should just tell me the Python version, hopefully. Right, perfect. Yes, sorry. Yes, of course. It just tried to run 789 rather than taking it as the input. Sorry, you are right there. And then what I should be doing hopefully this time I'll get the right output. Okay, so then it's doing the right thing because it's running, it's taking this as the command. Before it was trying to take 789 as the command of failing. Okay. Sorry, I have added more confusion by trying to do things on the fly rather than just doing it. So I apologize for that. And if we just, and then if we launch the container interactively, if you remember how we do that, just docker run minus IT shit on the end. And you can look in /home, oops, and the sum.py file's there. Now, if you modified sum.py in the container now, it would not modify sum.py on the local file system because this is a copy of the file that's been copied into the container image, not a map, not a mount of the file system into the container. Okay. So I could modify this here, but I would lose any modifications when I exited the container. Okay, sorry, do people have any questions there? I know I confused things by trying to be too clever, which didn't help with the explanation there. So we see two ways now to make data available within the container from outside the container. The first one is a runtime option, which means that you mount directly from the host, you mount data from the host into the container in some place. And the second one is a build time, where you copy data from the host when you build the image into the image, and then it's made available every time that image runs as a container. Okay, and they have slightly different use cases. Generally, the first one's for operating on live data and doing analysis and working with data, and the second one's for making sure that the analysis you're doing and the things you're doing the analysis are encapsulated properly within the container so they're reproducible and reusable by people. They tend to be the two use cases there. Okay, and the other challenge, I guess, with putting things in the container, as it does mention here, is it increases the size. So if you put them in a build time, it increases the size of the image. You could also, different ways of getting data into container are, rather than copying from your local file system, if it's available on the internet, either via Git or via a URL, you could use the run command, as we did. We used the run command for installing software using pip. Any command you can run like that within the container, you could pass in the Dockerfile to run as well. So you could git clone a repository if you were doing that, or you could wget a file off the internet using, as long as those tools were installed already in the Linux that you're using for your container. Okay, that's the sort of what we wanted to cover in terms of the basics of getting data in and out and making images more complex. There are some more other options down here, which I'm not going to go through in more detail, but we have mentioned in the chat a bit, is, to make the script run as default, you can do what I did there, but you can't actually supply the options to it in the same way. But if you wanted to supply the arguments, as Elena said in the test, you use the entry point there, which means that it will take the options from the command line instead. That's the difference between the command and the entry point. Things is the entry point also takes command line arguments rather than trying to run them as commands from the Docker run command. Okay, so the arguments get passed to the sum.py script instead of trying to be interpreted by the container itself as commands they should run. And you can also do things like editing environment variables. If you understand what paths are and you're familiar with paths, then you can add your commands to the path, and that means that you don't need to specify the full path to the script when you want to run it, things like that. But if people have more questions on those options and things like that, I'm happy to answer them probably towards the end of the day. Yeah, sorry, no, nasty questions are good because they make me think harder about what I know. Right, fine. So there's two separate questions here. One, I would have to test. Okay, I have to admit I haven't tested the one with the path in because it wasn't particularly interesting to me. So it may be that just the command or the entry point is missing from that example. If so, I'll fix this. As I said, this course is in development a bit, so I'll double check that and test whether that works or not. Okay. When you build an image, it only considers files that are on. Yeah, okay. When you build an image, it only considers files on the same level as the Dockerfile. So that's not strictly true. That's just because I didn't give it a path. Okay, so without a path in front of it, it looked in the current working directory where so it can get files from there. If I put sum.py somewhere else in my file system, say the directory above, I could have passed copy /sum.py into /home. Okay, so I could put the Dockerfile wherever I want. You found the absolute path from somewhere else and it failed. So maybe it can't go up, maybe that's a security. And let me try that. So try exactly that. Files in my code, sorry, don't know my muscle memory there. Let's try that. See what happens, shall we? Okay, so forbidden path outside the Go context. So I've learned something as well then. I had never actually tried that before. So it sounds, so the things you want to include either have to be in here or in subdirectories of here, I guess then. So let me make it the IR scripts. let me try taking it down a direction instead. My suspicion is that this will work. Let's see. Okay, so that worked fine. Okay, so that was useful clarification. Okay, that you can't take files from an arbitrary location within your file system. You can only take things that are in the current working directory or below, or in subdirectories of the current working directory, I guess for security reasons. And when you're building. Did I miss questions back up? I know Jeremy just said something. Can I recap on the solution for sum.py because somebody was in the room? So somebody was out of the room was being helped with something else at the time. Yes, so when I put the command as, sorry. When I did this, okay, and then tried to run the Docker container and pass it numbers to sum, what it was interpreting, because this was a command and not an entry point, it was interpreting the numbers as the commands to be run by the container, okay? And so was just trying to run them as BER commands instead of passing them through to the sum.py script. If I'd wanted to pass them through to the sum.py script, you need to do this trick. You need to use entry point instead of command. What that says is instead of interpreting anything I passed you on the command line as things to run, pass them instead to the command I'm giving you here, that I'm defining here within the container. Okay, that's the subtlety here. I maybe should just clarify because it was this v1 and v2 and v3 stuff at the end is to distinguish containers that are have the same name, they do the same thing, but they're different versions of it. I tried different things, so it's so people can, it's a more nuanced version of containers. So when they're pulling from Docker, they can say, I want v4 because I know it behaves in that way. And you could tag some things as, different releases. You can tag them as a release or as stable or as development and things like that, which we were talking about before. It's just gives you more flexibility in naming and making things available to people. And so we're supposed to have a 15-minute break now until we've got the two last sections of the course. I will double check that command entry point thing with that test one, and I'll do it live on the screen here. So people are getting a cup of tea and want to come back and watch, and I'll recap before we start with the next session on that. So one thing I did want to highlight was that some people have been having some sorts of issues if you're using Git Bash and Docker Desktop on Windows, problems with commands inside containers. Then there's a suggestion at this link that helps fix things. Thanks for this and the helpers for working with people to try and untangle that and get it sorted out. There's also noted in the chat about being able to check what commands set for a container after we had some discussion about what the command available was in the container, how you can check what command is actually set into a container, because from the tests we did, if one of the earlier layers has a command set or one of the parent images has a command set, then they can just inherit from that. It doesn't actually need to be built. It doesn't actually need to be specified in the Dockerfile itself. But there's a useful command there that you can use to inspect what the command is set in the current image. Okay, so let's get back to the course. One thing I did want to clarify after that session, because there is the subtlety about when data is available and at which point data is available. We covered two things there. I just want to remind this, and sorry if I feel like I'm going over this ad nauseum. But one was making data available at runtime, which is generally data that will be used as an input to analysis or some research or some work you're doing, and data that will change as an output. And you do that by mounting a file system from the host within the container, or mounting some sort of storage for the host inside the container. That means that when you operate on that data, it will change. permanently. And if you go back to the host after the container's finished running, the data will be changed, okay, which is generally what you want, generally what you want, or often what you want in that situation. The second thing we looked at, where we copied the script in at build time, means that if you change that script at when the container is running, which you could do by logging in, for example, and modify and editing it because you've got root privileges in the container, then those changes only persist while that container is running. As soon as you stop or exit that container, you lose those changes, because that data is a property of the image, not a property of the host file system at runtime. The way I try to keep it clear in my head is when the data is made available is it made available to the container at runtime, or is it made available to the image at build time? And that gives you, if it's the build, if it's the image at build time, then that data is in some sense static. It's part of the image itself. If it's at runtime, it's more dynamic data that can be modified and acted upon by the container and changed. Okay, so it can be a bit confusing when you first come across those two different styles of making the data available. Right. So that was our break. That's just finished. So I've got two sections left to try and finish off before we get to 4 o'clock when we're about to finish. The first one is just a quick demo to show some sort of power of containers. Now, it's not a demo that's an example from research, though I'd like to put one of those together as this lesson gets developed and as we improve the lesson going on. But it is an example that shows how a Docker container could be used in real life. Okay, so in this example, what we're going to use is a Docker container to display the website actually that you're looking at here for this lesson. Now, this lesson's generated based on a set of files using the template and uses a piece of software called Jekyll that turns these source code files into a rendered website. Okay, and Jekyll itself is a really complicated piece of software that has a complicated set of dependencies, and it's actually quite hard, can be quite difficult to install and get running on your local system. And one of the things that this demonstrates is the power of Docker to just forget all that dependency nonsense and just use a Docker container to mean that you don't have to worry about all that installation and making that sort of stuff work. Jekyll's based on Ruby, so you'd have to have Ruby installed, and then you have to have gems of certain versions and bundler and all these sort of things, and you can just get rid of all that headache by using Docker. So there's some steps here. You can either follow along if you want, or you could do this at your own time if you want as well. But I'm going to work through it here. So we're going to actually get the source files from GitHub that contain the files for this website. So I'm going to go to this link. I'm also going to go up a couple of folders. So I did the top. Sorry, if we go into the Docker intro one. So there we go. So this is where we had the basic some subdirectories. Okay. So I've followed this link to this website. And so this is the source code within GitHub for this lesson that we're actually following today. And on this green pull down here, there's a download zip option. So I am going to download the zip file. And then I'm going to get my file browser up, and I'm going to copy my, that was silly of me. Sorry, I've got my windows organized in the wrong way. So let me get this over here so I can actually drag and drop it. So I'm going to drop this thing that I've downloaded, this zip file, over into this directory here, which is the same as this directory I have here. So there's the zip file that I downloaded, and then I'm going to unzip it. Okay, and that should have created a directory called Docker Introduction GitHub Pages. Doesn't matter why it's called that. Let's just go into it. And this contains all the source code for being able to render this lesson in a web browser. But there's two things you need there. You need to be able to have the tool, the Jekyll software, to put it all together and convert it into HTML into the website. And the Jekyll software also provides a little MIDI web server so you can preview changes locally. So let's go back over to our actual lesson. So I've done all these steps and unzipped it. And we've listed the files that are in there. Okay, so we're up to this step now. So now I'm going to get get the Jekyll Docker container and run it. So let's have a look at let's break down this command before we run it so we can try and understand where we are and what we're doing here. So there's the Docker run, okay, run the container. --rm, we've mentioned before, that automatically deletes the container when it exits. Okay, so it doesn't sit around in our stopped exited container list clogging things up. There's interactive here. I'm not quite sure why that's there, but we'll try it with and without that when we run it. I don't know why it should be an interactive shell. I think it's because we need to keep it running to run the web server in the background, but we'll double check that. There's -v, remember, which mounts data from the host into the container itself. And in this case, we're going to take our current working directory. It's got curly braces around it this time. That doesn't really matter. PWD can have the curly braces or not have the curly braces. That's a matter of taste. It's been mounted into /srv/Jekyll in the container itself. This is this -p option is a new option. We haven't come across it yet. This is for mapping ports. So if you have a website, you need a port to be able to display it on, so you know where it's going to appear when it runs. And this says map the port on our host 127001, which is localhost, which means just display it locally within your laptop. Port 4000 to port 4000 within the container, which is where it will serve the website to. The name of the container is Jekyll. That's the official Jekyll release, and it's the latest release of Jekyll itself. And then finally, there's the command we're running within the container, which is Jekyll serve. Jekyll serve is a special command within the Jekyll software that builds the website and then sets up a web server so we can actually view the rendered website. Okay, so it's quite a complicated command, but I'm going to copy and paste it. It may take a little while to run because it's quite a big image. So let me do that, copy and paste it, and try running it. And let's see what happens here. So the first thing it did was it said, I can't see Jekyll locally, so I'm going to have to go and get it from GitHub. And you can tell this is a more complicated container than we've used before, because it's suddenly all these different layers are downloading and extracting. Okay, what you'll see is that Docker, because it knows these different layers of different downloads and different extractions, it can run them in parallel. Okay, so it tries to run them in a way where it can best utilize the bandwidth you've got and the compute power you've got. And so by far the longest one to run is this final layer here, which is very large. It's 225 megabytes, so it takes quite a while to download. Let me switch off my video for a moment. That might speed things up a little. Just for a moment while this is downloading. That will hopefully improve the performance of the download a little bit to make things a bit quicker here. You should hopefully still be able to hear me speaking. I'll put my video back on once it's downloaded, because that's the only thing it's impacting. Okay, there we are. So my video is coming back. Unfortunately for you all, you'll have to actually see me again. And now it's extracting that download. So this is a compressed download, all of them compressed downloads, so it has to actually extract the image from the compressed download. So off it goes. Let's take a little bit of time as well, again, because it's quite a big it's quite a big image, or a big image layer. I don't know if this means I need to get a faster computer, or if I just need to have more patience. Okay, we're over halfway there now, so it shouldn't be too much longer. Once this is extracted, what you'll see is it should start up the image and install all the bits that are required by Jekyll. Okay, So generally, how can you decide if a port is needed or what options you use in Docker 1? So actually, the most useful place to do that is to look at on Docker Hub at the examples of how you use the images. Usually, as I said when we were looking at the Docker Hub thing, actually their examples are really, really useful. Okay, so generally they're pretty well documented. So if you went and looked at the Jekyll one, it would show you examples of the command depending on what actual scenario you had and what you wanted to use Jekyll for, whether you're using it to serve, whether you're using it to build, and those sorts of things. And the same for other images. Of course, the other place you get things is on the internet, of searching how to do things on the internet. So Stack Overflow and these sorts of sites are really useful for those sort of things. Generally, in a more sort of, maybe a more structured answer to that is that it depends what you're doing, right? So if your piece of software you're using needs to serve some sort of web interface or yes, generally web interfaces, or needs to communicate with some sort of external resource across the internet, then you may need to expose a port to allow it to do that. But for often when you say you've got some sort of Python or R analysis pipeline, then often you won't need a port for that. If you know if it's a script within the container image that runs on a piece of data on your computer, then there's no port needed for that. Okay, and there is a bit of trial and error in terms of, you know, how what options you need and what options you don't need in things. And as you get more experience using Docker, you get a better idea of what the options might be and what might be missing when things don't work and things like that. And the other, you know, asking the internet, asking colleagues who have experience with it, and reading up how other people have done it are generally the way to learn these sorts of things. And certainly that's how I've learned. You know, is trial and error and experience. I mean, I've been doing that since I did my PhD and stuff like that. That's how I learned programming and stuff, was just trying things and seeing what happened, and seeing how you get on, building up that experience, and then asking people who are more knowledgeable than yourself about what you've done wrong and things like that. So now it's on to the stage of it's downloaded all the container stuff, so now it's working within the container to install all the dependencies that are required to make Jekyll work. So this is actually all you can see this is Ruby. So this is using Ruby gems, which is I guess is similar to pip or conda for Python, and it's a repository of different things that you can bring together to resolve the dependencies between the software. And this is the bit that if you try to install Jekyll yourself on your local system, that often gets stuck at with conflicting dependencies and that sort of dependency hell we've talked about. And what's happened here is that the people who provide the official Jekyll images have done all that legwork for you. They've resolved all those dependency issues and bundled up all that information into container images, which they put onto Docker Hub, and saying, here's a known set that works together and set up to install and work for you. So you don't need to work out how to do that yourself. You can use the Docker container to do that. And it's still downloading and installing stuff in the back end. So I'll just leave that running for the moment. I'll go back to there, and then when it's finished, I'll show you what it's done. So this is the script we've been seeing here. So it's installing stuff, and then eventually it should get down to the bottom, and we'll see appear in my terminal window this last bit that says it's built the website, and it's provided a server address where it's being served to, that we can go and look at to see the rendered website and see what it looks like. And we'll do that in a moment once it's finished. And when we see it, it should look very similar to the website we're actually using on GitHub pages at the moment for this lesson. And if you make a change, the other thing you can do is you can make a change to the data, and that should automatically be updated in the thing. So you can develop the website and develop the content. And this is what we do when we're updating the content in the lesson, is we'll update things and then use Jekyll locally to check that it's rendered before pushing it up into the public repository for people to download and use themselves. Okay. So, but I think the idea here is not that you know, you're going to be using Jekyll to build websites and things like that. It's to show you that there's something really complex, a really quite complex piece of software with lots and lots of dependencies that can be a real pain to install. And although it's taken a bit of time with Docker, actually, the time I've used here has been minimal compared to fighting through the dependency hell to get this up and running myself. Okay, so it's still just generating the website, so I'll leave it there for the moment. And that's what let's try and illustrate the power of Docker here, is that somebody else or other people have worked together to solve that dependency issue and then provide a packaged solution that should work wherever, whichever computer you're on. Because I could do this now, I can use Jekyll. You know, if I switch, this laptop breaks and I get a new laptop, I don't have to fight through reinstalling Jekyll again. I just get the Docker desktop installed and I'm up and running again straight away. If I want to work with this sort of complex software, and the same is true of any piece of complex software. So I'm going to take that web address and I'm going to paste it into my web browser. So this is a web server that's running on my local laptop, not out on the internet somewhere. This is just a local. This is local host and is being displayed from within the container itself. And then you can see it's too small to read, but this is similar to the lesson you've been doing. It doesn't have the singularity bit in actually, because they're actually can be combined into one lesson as we're doing for this course, or in two lessons. So this is just the Docker section of the course. And so there is, it's running there. I can finish that, and then I can Control-C here. Get the server to stop and get back to my prompt. And that means the container has now stopped, and because it had the --rm, it's been deleted as well and tidied up. And anytime I want to rerun the Jekyll, I can rerun this command. In fact, this is a command that I use so often in my work day to day that I actually create an alias to it, so I can use it again. Okay. Where's the original website? So what was the IP address? It was 0.0.0.4000. It's here, or localhost : 4000 or 127.0.0.1 4000. They're all aliases to the same place, which is just localhost port 4000. Just out of curiosity, where's the original website's container running? Well, you can see. So if I go back to the original one, it's here. If you look at the URL, you'll see it's on GitHub. It's GitHub pages, github.io. Okay, so GitHub pages actually has Jekyll built in. So any website you write in Jekyll can be automatically rendered and built by GitHub pages. That's one of the reasons we use it. That's just one of the reasons carpentries use it for their template. It's because it's easily hosted on GitHub pages, which you can automatically generate from a GitHub repository. Okay, so the idea of that session was just show you how a complex sum of dependencies issues can be resolved by using containers. So the final bit before we finish up, we've got about 15 minutes left. So the final session is, we've talked a lot about containers and the practicalities of using containers throughout the day so far, and how we actually build containers, how we run containers, Docker containers. And we've mentioned reproducibility along the way in a few different contexts and in passing. But this last section wants to we'll try to take a look more about the issues of reproducibility themselves, and how you make container images to make my research more reusable, and how can you can incorporate containers into the research workflow. And then at the end, I just mentioned some container orchestration tools as well. So one thing I want to say right at the start is that reproducibility aspects of software and containers is actually really still a very active area of research, right? There's no accepted way to make software reproducible, or this is the way you make software reproducible, or containers reproducible. So there's a lot of discussion and development are ongoing at the moment, and will be subject to many changes in the future and how things evolve. I'm going to present some ideas here, approaches here, but best practices will evolve in the future, and new services will evolve to enable reproducibility in software and containers and things like that. And I think, first of all, what we really need to do is define what we mean by reproducibility here. What I mean, of course, you may or may not disagree with what my definition of reproducibility is, but this is the one I've been using for this course, is The ability of someone else or your future self being able to reproduce what you did computationally at a particular time, right? Be this some sort of research work, analysis, or something else. You want to be able to do that as closely as possible, even if you don't have access to exactly the same hardware resources that you had when you did the original work. And containers can help here, right? Because the same computational work we run across multiple different technologies seamlessly. You can save the exact process you used for your computational work rather than relying on potentially incomplete notes where you forgot to write down a step, or you have to actually munge the data in this way before you can use it. And you can have a proper verifiable record of that. You can save the exact versions of the software and the dependencies in the image. Now that's not the same as complete reproducibility, because hardware does have an effect. And if the underlying hardware changes and the underlying Linux operating system changes, there's still the potential for changes in reproducibility there, but at least you eliminated some of the variables. You can have access to legacy versions of software and their underlying dependencies, which might not be available anymore for download, but they are encapsulated in your image. And this is one of the reasons we spoke earlier also about sharing the Dockerfile or sharing the image and what the differences between them are. If you had the Dockerfile, but those versions of software that are encoded in Dockerfile to be installed are not available anymore, then the Dockerfile is not much use to you. If you have access to the image that has those bits of software built into it, then you can potentially still do something useful here. Depending on the size of the data, you could also potentially store copies of key data within the image to make sure it's saved and available, and you haven't lost that in the future. And you can archive and share the image, which we've seen. Well, we've certainly seen sharing already using the Docker Hub, but you can also archive it, and you can associate it with a persistence identifier, much in the same way as you do with, for example, a paper using a DOI, a digital object identifier, to allow other researchers which can reproduce, cite, and build upon the work. They can even cite that they used your particular container or your research workflow encapsulated in a set of containers. So, we've already seen, as I mentioned, the Docker Hub provides a platform for sharing images publicly. And once you've uploaded an image, you can point people to its location. They can download and build on it, and that's fine. For a day-to-day basis, working collaboratively with people in an active project, and that works fine. But it's not a good option for long-term archival image in support of research and publications, as the free accounts have a limit on how long the image will be hosted. If it's not updated, it will just be zapped and deleted. It doesn't support adding persistence identifiers to images, so Docker Hub could change their URLs, and you might not be able to find the image again in the future. And it's easy to overwrite tagged images with newer versions by mistake and lose the exact copy you wanted. So you can archive images in a different way. For example, some of you may have come across Zenodo before, which came out of the work at CERN, which is a way of storing digital objects long-term and associating persistent identifiers with them, and people can cite them and track, and they can be tracked. And the way you could do that is Zenodo supports archiving, the archiving of what are called tar archives. That's a common format for data archiving within Linux, Unix, anyway. And Docker images can be captured as tar archives using the Docker save command. So, for example, if we wanted to export an image we created earlier in the lesson, we could use the Docker save command and give it an output file name. So let me get the Docker image. And that's up. And so I'm going to do Docker save Alpine someone. Want of a better choice, and I'm going to give it an output file name. So it's asking about the impact of using ---- network instead. The short answer is I have not looked into that and don't know the answer to it, but I can look it up and come back to you tomorrow with some answers for that. So unless one of the helpers knows off the top of their head or can answer it straight away, then I'm happy to research what it is and look for it. Okay, so that's finished now. And if I list my file, I've done it in this. I've done it in here, which is a pain in the neck because it's really hard to pick out where the file is because I was in that wrong directory. But you can see here, it's created this 114 megabyte file. Now, there is a limit on upload size to Zenodo, so it's often useful to zip it up using something like gzip to create a smaller file, which you can then archive. Now, I'm not actually going to show the archiving here. Well, maybe I could actually. Maybe I could. In fact, let's do that while it's gzipping. So let me show you Zenodo. I'm going to use something that's called the Zenodo Sandbox, which isn't the standard Zenodo site because it doesn't actually go ahead and create the persistent identifiers. It's a place you can come and test uploads, okay, without creating all the infrastructure associated with it. Because if I used actual real Zenodo and uploaded stuff, that's it there forever. Okay, so what I wanted to do was do something that's not as permanent, because I'm really just messing around here. So I'm going to move that archive file out of this directory because this directory is the wrong one. So I'm just going to move it up. So you can see that I've created this tar archive. It's now gzipped, so it's only 49 megabytes instead of the 114 or whatever it was before. So I've logged into Zenodo. I've got a Zenodo account. It's actually linked to my GitHub account. So if you've got a GitHub account, you can easily link it to your Zenodo account. And then I can do new upload. Yeah, oops, not to Chicago COVID response. Sorry, that's not what I meant. Let's go to upload here. Okay, you can see I've done one a while ago as well. So I can, it's a pretty standard web interface. So let me take my file and drop it there. Okay, and it's 48 megabytes. You can add it to a particular community if you want them to. There's some communities already there. You can say what it is. In my case, it's a piece of software. Have you already got a DOI? No, then they'll assign one to you. Publication date, I'm just going to select today. Test. Give it some basic information. I need to give it my location. So give it the University of Edinburgh. It's got my address, and you can add other. And there's lots of more information, right? You can say if it's open access personally, you can give it a particular license and all that sort of stuff. You can say where the funding comes from, and there's lots and lots and lots and lots of other things. And then you can save it. And the author's not valid ORCID identifier. That's ORCID, that's why. I don't have an ORCID ID to put in there. Okay. That was just me trying to be too quick. Saving that again. It still didn't like something. Okay, so it's not. I'd have to go and find my ORCID identifier, which I can't remember off the top of my head to do it. But you can see the process. You can add a file, you upload it, and then what you get at the end is something that looks like this. Well, here's one I did earlier that has the tar archive for the container and has more information about it. And you can add new versions, you can add more data about it, and you can get the information. It's given me, because I didn't enter a DOI, it's given me a DOI. In the sandbox, this isn't a real thing, but in the real life, you can get a real thing which you then use to cite the container. And that helps with the reuse and reusability and reproducibility of the thing. So, and then once you've got that tar archive, of course, you can get it back into Docker using Docker load. And you can use it from the gzipped version of the archive to get it back in. So that's just one example of how you can potentially take a container that you've created, create a permanent long-term record for it with a persistent identifier that allows people to cite and allows people to reuse it in the future. So in terms of reproducibility, good practice. So making the use of images, computation and computational environment required for your work. If you have a container where you have to log in, where you have to access it interactively, add some extra stuff before it all works properly, then that's not really capturing the environment you used, right? So you should be trying to capture in the container image the environment that was used as much as possible. The next one is a slightly tricky one, is that we've sort of touched on a few times throughout the day, is depending on the appropriate granularity for the images for your computational work. You know, and this is going to be different for each project, research area, or things you're working on. So should you have lots of small containers, each that do an individual step in your workflow, or should you have one large container that contains all the tools you need and is able to do the whole of your workflow in one go? Okay. Now the second one's, the large container sounds great because, you know, it captures everything and everything's known to work together, and you're not going to have any dependency issues and all that sort of stuff. And here's a monolithic thing that does this and that piece of analysis. But the smaller ones may be more useful because they can be coupled together in different ways to do slightly different analyses and reused more flexibly, and are also smaller and so are easier to handle and pass around and share with people. Document what you've done and why. Put in the comments in the Dockerfile or the use of the image describing, you know, give people the context of why you made that decision. And it's not just people, it's you in the future when you come back to it, to understand why you made the decisions, what you did. When you're publishing the work, use the archiving DOI service such as Zenodo to make sure your image is captured as it was used for that work in that state. Okay, because you may change that image over time if you go on to do further work in that sort of area, but then you've got a snapshot of what you actually used to do that particular piece of analysis that you published or made available to the community. So there's just some of the ideas of good practice at the moment. We talked a bit about container granularity and about containing a single container image of all the tools you require, or many container images running single commands or steps of the workflow. And most things actually sit somewhere between these two extremes. And, you know, there's a small exercise here to think about the positives and negatives that we don't really have time to go into this afternoon, I don't think. But just to give you an idea of what the sorts of things we're thinking about here. So with a single large container, some of the advantages may be it's simpler to document. The full set of requirements are packaged in one place, and it's potentially easier to maintain. Though it could be the opposite if you're working on with a large distributed group with lots of researchers, you know, with lots of people having to input it into this one monolithic container. The disadvantages are, we've already mentioned, could be very large inside, making it difficult to distribute. You can potentially use Docker multi-stage build to reduce the file size. Singularity also has that sort of feature. You could end up with the same dependency issues within the container from different software requirements. So say, you know, it does two bits of analysis, slightly separate bits of analysis using R, and they have competing requirements on the dependency within the container. Then you're back in dependency hell, because you're just trying to create one big computer that can do everything again, which may cause challenges for you. It can be potentially more complex to test to make sure it's working properly, and it's less reusable for different automated work. For the multiple solver container, the advantages are the individual components can be reused for different but related work. The individual parts are small in size, making it easy to distribute it, and you can avoid these dependency issues between different softwares within the container itself, and it can be easier to test. You can probably imagine how you can write unit tests more easily for these small independent containers. The disadvantages, I guess, are more difficult to document how you use them. You have to be more specific in how they're used together. Could be more difficult to maintain, but if you're working with a large distributed group, this might be a positive, because different people work on different bits of the workflow independently. And you can end up with dependency issues between the component containers. So if they get out of sync, and you know, people are picking up slightly different versions of the different containers for the different bits of the workflow. So these are the sorts of issues that people should be thinking about. And one thing I would say is that, you know, a small amount of planning at the start of a project goes a long way. You know, so so rather than diving in and just letting things evolve organically, having some sort of strategy about whether you're going to use a single big container or what granularity you're going to be using and those sort of things, and taking the time to think about that and what the implications are for the project you're working on at the start, is time really well spent. And if you need to talk through the issues and get advice, then talking to people can help you out across, particularly across the UK, US, and Europe at the moment. There's the research software engineering movements, which I'm part of, and a lot of the helpers here I've been part of as well, are people with expertise in research software, for used in a research context. And most places now have some sort of local RSE group that you can go to and ask for advice. And this is exactly the sort of thing you can ask for advice on. Okay. So the final bit in this section was a bit about container orchestration, and this ties into splitting up your workflow into multiple smaller containers. You can do things manually and make things work together manually, but there are a number of container organization tools that can be useful that are beyond the scope of this course to look into. And the one you've probably heard of the most is Kubernetes, which came out of Google, and they used to orchestrate different parts of not a research workflow, but their production workflow generally across the Google scale of internet service provision. But there are other ones, Docker Compose and Docker Swarm, that can be used to orchestrate rather than just think about individual containers and then bolt them together manually. Think about how they can be built together, managed together, linked together, and make sure they work together with passing data between each other properly. Now, if reproducibility using containers was sort of an open area of research and active, and there's still a lot of active at the moment, this is the Wild West, right? I mean, people have used these container orchestration tools a lot for provision of things like web services and services that Google provide and things like that. But for their use in a research context is much newer and really is a really very active area of people looking at things. And so if you tend to go down this route, you may find that there's not huge amounts of information over there on the internet. Now, I have provided there are some examples, right? So Docker Compose has been used, for example, deploying integrated drug target screening platforms. So you can read an example of how they've done that. But the other ones just have links to what is Kubernetes and Docker Swarm. What I would say is, if you're interested in these areas, doing some reading and then speaking to an RSE about your requirements and what you want to do is the right way to go. Yeah, and finding a local RSE. If you're struggling to find a local RSE, I know it's sort of with the context of this course, but please feel free to get in touch with me. I'm happy to help you out there and put you in touch with the wider community. I can probably find out who your closest RSE group is and things like that. You can talk to via the wider community. And I know Will and Jeremy in particular are both closely associated with the RSE organizations as well. So I'm not going to go into any detail about container orchestration tools. If you're interested in that side of things, then please let me know. We have a follow-on session in a couple of weeks, or maybe just in the new year after this course, for you to ask any questions that have come up in the meantime since leaving the course, and we can look at those sort of things then if you're interested in them. Okay, so that is the end of today. Now, I realized the last bit, particularly about the reproducibility and the orchestration and things like that, is sort of a bit more not a solution, but a pointer to where to start thinking about these things. And like I say, we're happy to follow up with any questions on those sort of outside the course and beyond. But what I didn't want to do was run over very, very far over the finish time. We're only 5 minutes over at the moment. But I hope you found today useful and interesting about Docker. And I look forward to seeing you tomorrow for the Singularity